Welcome students. In this video we are going to study about modern periodic table, and that will start with modern periodic law. Modern periodic law says that periodic properties of elements are the function of their atomic numbers, and based on this we prepared a periodic table which is known as modern periodic table, as it is followed today also. We will have a detailed study of modern periodic table. All the rows and all the periods will be studied in more detail. We'll see how the elements are classified according to their electronic configuration as S block, P block, D block elements. What is the situation of metals, non-metals and metalloids in the periodic table. We'll see how the electronic configuration vary in a periodic table, and also we'll study the IUPAC naming of the elements with atomic number greater than 100. So let's start. Modern periodic table. After the failure of Mendeleev's periodic table, a new periodic table was produced which we follow till today also, and that is known as modern periodic table, which is based on another law which is called modern periodic law. And according to the modern periodic law, the properties of elements are periodic function of their atomic numbers and not atomic masses. Mendeleev's periodic law stated that properties of elements are periodic function of their atomic weights, but according to modern periodic law, the properties of elements are the periodic function of their atomic numbers. That means when we arrange the elements in increasing order of their atomic numbers, we find that the properties of elements are repeated after a certain interval, and that's why it is called that properties of elements are periodic function of their atomic numbers. And this periodicity in the properties is actually due to the repetition of the similar outer cell electronic configuration after certain regular intervals. And this is how modern periodic table looks like. You can see that there are some horizontal rows, and these are called periods. These are periods. So there are a total of 7 periods in modern periodic table. 1, 2, 3, 4, 5, 6 and 7 periods. Apart from that, there are some vertical columns also, and these are called groups. And there are a total of 18 groups. First, second, 3, 4, 5, 6, 7, this is 8, 9, 10, 11, 12, this is 13, 14 group, 15, 16, 17 and 18. These are actually the 18 groups, and these two rows which are present at the bottom are the extended form of periodic table, and we will discuss about them later. Okay. Now apart from these, now these elements are classified in some groups, and these starting the two groups are called S block, or these elements are called S block element. These are called D block elements, and these are called P block elements, and these two which are present at the bottom are actually F block elements. F block elements. The question comes, why? This is the classification of elements on the basis of electronic configuration. Okay. If you write the electronic configuration of any element in present in S block, you will find that the last electron enters S shell. Let's write that for lithium. Atomic number is 3, and it would be 1s2, 2s1. For sodium, it would be 1s2, 2s1, 2s2, 3p6, and then 1s2, 2s2, 3p6. It is 1s2, 2s2, 2p6 and then 3s1. So what we find that in all the elements which belong to S block, the last electron enters S subshell, and that's why these are called S block elements. Similarly, in P block elements, the last electron enters P subshell, and that's why they are called P block elements. Okay, let's write the electronic configuration of boron. It would be 1s2, 2s2, 2p1, last electron entering P subshell. If we write that for oxygen, let's say, it would be 1s2, 2s2, 2p, 2s2, 2p6, and then we are left with, okay, its atomic number is 8, so it would be 2p4. So last electron is entering P subshell. So whatever is the element of P block, when we write its electronic configuration, we find that last electron enters P subshell. So in D block elements, the last electron will enter D subshell. Let's write that for scandium. We find it 1s2, 2s2, 2p6, 3s2, 3p, 3s2, 3p6, 4s2, 3d1. Is this so? It is 21. So up to here it's 10 and 20 and 21. So last electron is entering D subshell, and similar will be case with F electron. So S orbitals are those, S block elements are those in which last electron enters S subshell. P block elements are those in which last electron enters P subshell. D block elements are those in which last electron enters D subshell, and F block elements are those in which last electron enters F subshell. So this is the classification of elements in modern periodic table based on electronic configuration. Okay, now these are called S block, P block, D block, F block, and these F block elements are also called, the first one is called actinoid, second one is called, the first are lanthanoids, second are actinoids, and these are placed actually outside the periodic table. If you see, it is starting from 58, and if you look for the 57, it is lanthanium, and after that it is 72 hafnium, and that means there are some electrons missing from between these two, and it is actually from this to this. So the first row belongs to this position after lanthanium, and similarly the second one belongs to this side. And now why they are placed actually outside the periodic table is to maintain periodicity. It was observed that if these are placed within the main body of periodic table, we find that the properties of the periodicity of the properties of elements gets disturbed. So it's better to keep them outside the periodic table, and we study them separately because they all have some certain specific properties. They all have some common properties, and these are called, first one is called lanthanoid series, second is actinoid series. So this is actually a long form of periodic table. So we have just discussed the classification of elements on the basis of the electronic configuration in modern periodic table. Now these groups and periods do have some hidden information in them, and what is that? The first is all the elements which belong to same group. All the elements which belong to same group have same equal number of valence electrons, have equal number of valence electrons. This one, the elements of first group would have one valence electron, that means one electron in their outermost shell. Here it would be 2, here it would be 3, here 4, then 5, then 6, then 7, and these are actually, they do not have any, these have filled electronic configuration, filled stable with 8 electrons. So, and these have, again, these are transition elements, they show variable oxidation states. So these are called transition elements, actually, transition elements. D block elements are called transition elements. Transition elements, and these S block and P block elements are called representative elements. Representative elements. So if someone asks you about representative elements, you know it is asking about S block and P block elements only, and these D blocks are called transition elements, and these are also, and these F block elements are called inner transition elements. Okay. So group gives us information about number of valence electrons. If we are talking about group 4 elements, we know they will have 4 electron in their valence shell. Now what is about periods? Periods give us the number of principal quantum number n, the number of shell. Those elements which belong to the first period will have n is equal to 1, that means only one shell. Those belonging to second would have 2 shells. Those belonging to period 3 will have n is equal to 3, that means 3 shells, and so on. Those which belong to 4, that means if we are talking about bromine, and we know bromine belongs to 1, 2, 3, 4th group, actually 4th period, and 7th group. That means it has 7 valence electrons, and it has it has 7 valence electrons, and there are total of 1, 2, 3, 4 shells, because it belongs to 4th period, that means 4 shells are there, and a 7th group, that means the valence is 7. Actually it belongs to 7th group in representative elements. The first group of representative elements, second is the 3rd, 4th, 5th, 6th, and so on, and we just ignore transition elements while talking about valency. So again, group gives us about the number of valence electrons and also valency, and period represents the number of shells. Great, number of shells is equal to number of periods. Now next thing is about metals and non-metals. Actually those which are all those elements which are present on right hand side are non-metals, generally non-metals, and these are metals, and also these all are metals. These all are metals, and these are non-metals. While there are some elements like boron, silicon, and these all which actually belong to technetium, protium, cadmium. These 1, 2, 3, 4, 5, 6, 7, 8 elements are metalloids, because these have the property of both metals and non-metals. Now why these are metals and these are non-metals? We know that if we talk about the S block element, it would have 1 valence electron, and in this it would have 2 valence electrons. So we know for metals it is very easy. Metals are those which release 1 electron. Okay, let's write down the electronic configuration of lithium. It would be 1s2, 2s1. Now for getting and again it would be 1s1, 2s1, and 2p0. So in order to get a filled noble gas electronic configuration, it either has to accept electrons in s orbital also and p orbital also, or it can, rather than release 1 electron, so it will become 1s2, which is a stable. So those all elements which are present actually on left hand side of the periodic table release electrons easily, first because of their larger size, second because of presence of less number of valence electron, they can easily donate them, and that's why these all are metals. While non-metals, if you see here, fluorine has 7 electrons, it requires only 1 electron to complete its octet, rather than releasing 7, it will accept 1. So those which are present on right hand side, extreme right, are mostly likely to be non-metals. Why? Because they are of larger size, so it is not possible for them, they are of smaller size, so it is not possible for them to release electrons, and secondly, it is all about gaining electrons to get stable electronic configuration. Okay, I talked about size. We'll discuss about size in later slides and how size varies in a periodic table. So all you need to know here is that metals are present on left hand side, non-metals are present on right hand side. In between them there are metalloids which show property of both metals and non-metals. So this was all about Next is IUPAC nomenclature of the elements with atomic number greater than 100. Actually, there are some elements for those which are yet to be discovered, and they are not present in modern periodic table. So we know, if just like what Mendeleev did in his periodic table, that he left space for those elements which are yet to be discovered. In this modern periodic table, we also do the same. We left space for those elements which are of atomic mass greater than 100, and those are generally unreactive. So, and we follow a specific IUPAC nomenclature to name them. We know that there is an element which will have atomic mass of atomic number of 102. So we have left space for that, and we just predict its name using IUPAC nomenclature. So this slide is about IUPAC nomenclature of the elements with atomic number greater than 100. So for this, Latin words roots for various digits are listed in the table given below. So there is a actually word root. For 0 digit, we call 0 nil, and the symbol is N. 1, it is U and Un. For 2, it is B. For 3, it is tri. For 4, it is quart. For 5, it is pent. For 6, it is hex. For 7, sept. 8, act, and N. And there are abbreviations. So we use these Latin words for various digits of the atomic number are written together in order of digits which make up the atomic number, and EM is added. Actually, what we do, let's say we have an element with atomic mass 105, and we need to write its name. So for first digit, we have UN. So we start the name with UN. It would be 04 nil, and 5 stands for actually pent. So we write these, and in end we have to write EM. So just add all these, and the name which we get is Young Nil Pent EM. And in short, we can write it U 0, it's N, pent it is P. So this is actually the symbol, and this is the name. This is how we write a name. Okay, if we want to write the name of 100th element with atomic mass 100, so we'll write 1 for UN, 0 for obviously nil, and again nil, and in end we'll use EM. So the name would be Yun Un Nil Nil EM, and the symbol would be UNN. This is how we write name of all those elements with atomic number greater than 100, and this is the table for those elements, for the name of those elements which have atomic number equal to or greater than 101. 101, 102, so you can write their name easily in this table. Now there is a solved problem based on this, which was asked in IIT-JEE in 2003, and it is a problem based on direct knowledge of the concept. Okay, so it says, according to the periodic law of elements, the variation in properties of elements is related to their nuclear mass, atomic mass, nuclear, neutron, proton number ratios, or atomic masses. So it is actually talking about modern periodic law, and we say, according to the modern periodic law, the properties of elements are periodic function of their atomic numbers. So the answer is B. So students, now you are aware of modern periodic table, and you know what are S block, P block, D block, and F block elements. We know what is the position of metals, non-metals, metalloids, and transition metals in the periodic table. We are aware of representative elements and transition elements, and also inner transition elements. So this all was about modern periodic table. In next video, we are going to study about periodicity in properties. That means how different properties of elements like atomic radius, electronegativity vary in a periodic table. Thank you.